right, this is lecture 2, where we're going to be talking about numbers and a little bit about math. Tilius. All right, so mathematicians work with numbers. Scientists work with measurements. Okay? A measurement is both the quantity and the unit. Okay? So when you measure something, it's not just 5, it's 5 meters long, or it's 5 grams of mass, or something like that. Okay, the measurement is both of those things at the same time. So sort of like the size of the object and its color. You cannot remove one from the other. Okay. Now, when it comes to the math, you can multiply and divide anything. 5 meters per second is 5 meters divided by 10 seconds, or 1 divided by 2, or what have you. Okay, and so that you can make a new kind of unit. 5 meters in 10 seconds, meters per second is the new sort of unit. Okay? It's a compound unit. But addition and subtraction can only happen if the units match. Okay? So 5 meters plus 4 meters is 9 meters. 5 ducks plus 4 bananas doesn't work. Okay? Now, sometimes units can be converted into other units. So that, for example, 5 kilometers plus 4 meters is what? Well, you have two options. You can convert kilometers into meters. Or you can convert meters into kilometers. These are more or less the same answer. Again, the units differ, which is why the quantity differs. So, the units have to be the same before you can add or subtract. Anything can be multiplied or divided by anything. Just remember that you're going to create a new kind of unit when you do that. Okay. Now, units really do have real-life implications. This here is an article talking about a big news event from 1999 when NASA accidentally destroyed a $125 million orbiter that they intended to go around the planet Mars. Because NASA, being a government agency, has to use the English or imperial system, feet, pounds, things like that. But their contractor was under no obligation to do so, so they used the metric system, which is a far better system. And nobody told either group that they needed to be careful about that, I guess, and so NASA just sort of innocently assumed that they were using the same units, and the result was a $125 million mistake. So pay attention to your units is what I'm trying to say. Now, I've mentioned compound units, such as meters per second. They can get fairly complex. Okay? So the watt is a unit of power. Okay, joules per second, or energy expended over time, right? But the joule is another compound watt. It's a measure of energy, that is to say, the Newton meter, okay? Force exerted across a distance per unit second, because we're still talking about power. Okay? But the Newton, once again, the measure of force, is a compound unit. Okay? Exert a force, you're going to cause a mass, kilogram, to accelerate, meters per second squared. When you combine that with meters and seconds over here, then you get the total number of basic units for the watt is actually 1 kilogram meter squared per second cubed, which in physical terms is kind of meaningless. Okay, you try to parse that, it's gonna tell you pretty much nothing. But when you turn it back into watts and joules per second, it actually does make some sense. Okay. So you're going to need to get used to seeing that sort of thing. It shows up an awful lot in science. Now, just a bit of a reminder, when you multiply, that means adding exponents. When you divide, that means subtracting exponents. So that means that, for example, 5 meters times 4 meters is 20 square meters. Okay. 3 cubic feet divided by 2 feet equals 1.5 square feet. Okay. So 1 plus 1 equals 2, 3 minus 1 equals 2. Okay. So multiplication means addition of exponents, division means subtraction of exponents. Now, like I said, the English system is stupid and you should feel bad for using it. We will be focusing on the international system, or the system international, because it was developed by the French back when they were still super powerful. It was devised to make units uniform across all countries. Because once upon a time, every location had their own unit, and it might be changed if a new prince came in and decided that he wanted to show off his power, things like that. It was kind of ridiculous. So the international system is just a way to standardize it, and with one exception, it's pretty much completely divorced from everything that came before. Okay, so the kilogram is the standard unit of mass. The second is the standard unit of time. The second is the standard unit of time, and the meter is the unit of distance. The second is the only one that, they couldn't really do anything about. As we encounter more standard units, we'll talk about them. Just get used to seeing them. Now, science as a whole causes a huge range of numbers. And from the distances between stars, the nearest star to us is Alpha Centauri, and it's this far away. It's a ridiculously large number. It's 4 light years, if you want to put it in something easier to say. This is the distance in meters. Okay. And the radius of the hydrogen nucleus is this ridiculously tiny number of meters. We use prefixes to make those numbers a little bit more manageable. Basically, these zeros don't tell us anything, and they're just sort of there to take up space. So we can get rid of them using prefixes. So this great big number becomes 37,840 terameters. This ridiculously tiny number becomes 1.75 femtometers. Okay, all those zeros are now sort of compressed into this tera. Okay, the tera tells us that it's a really big number. And this femto, likewise, tells us that this is actually a really small number. And they just make it possible to write these numbers without wasting ink and paper. These are the prefixes you're most likely to see. So here in the middle is sort of the standard. There's no prefix for just meter or gram. Okay, this down here tells us that that prefix means you multiply by 10 to the 0. 10 to the 0 is just 1. Okay. Kilo means that it's actually 1,000 times bigger. Mega means 1,000,000 times bigger, multiplying by a million, 10 to the 6th. Giga means 1,000,000,000. Tera means 1,000,000,000,000, 10 to the 12th. Over here we have centi, milli, micro, nano, and pico. Notice that centi is the odd one out. It's the only one that's not making a step of 3. That's just because it's kind of useful for centimeters. It's a unit of length that you see a lot. That's one of the few places you actually encounter. There's not all that many that use the centi prefix. Most of the time you're making a jump of 3 spaces. Or 3 decimal places, I should say. Another special unit is the angstrom. It's got that funny little circle over the A. That's 10 to the negative 10th meters, or 1/10 of a nanometer. That's about the length of a chemical bond. So a carbon-carbon bond is about 1 angstrom long. You see those occasionally in science, or chemistry specifically. Not incredibly often, but it'll show up occasionally. So if you see an A with a hat, then that's what you're looking at. Now, doing conversions between these numbers is not as terrible as you might think. So let's just say 32 grams. So let's take that to milligrams on the one hand and kilograms on the other. Okay, so you come back to this chart. Grams is right here in the middle. Milligrams is going from 0 to negative 3. the negative, there's an, I don't know, let's see, maybe the negative sign. Screw it, you're moving to the right. You're going from here to here, you're moving to the right. That means the decimal place is moving to the right. So 32, decimal place is right here, 1, 2, 3 spaces, 32,000 milligrams. So in this case, you're going from grams to kilograms, you're going to the left. The decimal place moves to the left by 3 spaces. So 32, 1, 2, 3, 0.032 kilograms. So that is how you can convert. If you have this chart handy, it won't always be handy, and it won't necessarily be written in this form. They might write it vertical, they might put the smaller things on the other side. I just write it this way because, honestly, it was a stroke of good luck, but it works really well for working out how to do these conversions, and it'll work regardless of where you start. Say megagrams to kilograms. So 3 megagrams to kilograms. Okay, you're moving to the right. Going from 6 to 3 means you're going 3 spaces to the right. Okay. So it will always work so long as you have the units written in the correct way and you have the numbers. There are other ways to do this conversion. I know that not everyone is great at math, though, so I'm trying to do this in a sort of visual way for you. The other way you can compress these numbers and get rid of all those pointless zeros is through scientific notation. For scientific notation, you just move the decimal, you keep the unit the same, and you use this times 10 to the something to indicate how far the decimal place is moved. Okay? So here, the decimal place starts here. You move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spaces to the left. So it becomes 1.23 times 10 to the 12th. Your goal is to get a number between 1 and 10. So 1,230,000,000 meters becomes 1.23 times 10 to the 12th meters. In the older notation, that would be 1.23 terameters. And it works in the other direction as well. You're moving the decimal place to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That gets you a number between 1 and 10. So 2.34 times 10 to the negative 10th meters, or 0.234 nanometers, or 234 angstroms. So which notation you use can be a matter of taste. We tend to mix and match depending on the situation. 1,540,000 grams is 1,540 kilograms is 1.54 times 10 to the 6th grams. Okay? This is another way of writing it. If you ever work with a spreadsheet program like Excel, you'll often see this E plus 6 or E minus 6 if it's a negative sign here. That's just E, just means times 10 to the. It's sometimes also a capital E. Okay. The big reason that we have largely, I think, switched over to scientific notation is because this is really easy for computers to work with. These old prefixes, they were devised, a couple hundred years ago when computer and calculator was actually a job title and not the name of a machine. So humans can work with these fairly easily. Machines can work with these very easily. That's not to say that computers can't work with these. They can. But it's a lot more effort than doing something like this. The bigger ones, we don't tend to use all that often. We either come up with special units like light years or tons, or we just use this sort of notation here. The smaller ones, we often just go ahead and use the scientific notation, but in some special cases like centimeters or nanometers or microns, micrometers, micron is another name for a micrometer, they tend to have their own special sort of usage in various niche fields. Like nanometers are often used for describing wavelengths of light, centimeters for distance is less than a meter, just the size of common objects. Angstroms, like I said, for bond lengths, things like that. Microns, micrometers are used to describe wavelengths of microwave light, and so on. You're going to have to be familiar with both, and you're going to have to be able to do math with both. These show up kind of all the time. Okay. Scientific notation. Okay. The math is not particularly difficult. Multiplication and division are kind of the easiest, so we'll start with those. So multiplication and division, scientific notation. Say 3.10 times 10 to the third divided by 2.0 times 10 to the second. Now, you might think this was really nasty, and you have to do that times that. This times this times this, or divided by this times this, and you worry about getting the order of operations wrong or something like that. Don't worry about it, because you can treat this part separate from this part. Okay. So 3.10 divided by 2 is 1.55, and then so you're going to subtract the exponents. 3 minus 2 is 1. So for division, you divide the numbers, subtract the exponents. Then for multiplication, you multiply the numbers, you add the exponents. And so if this were a multiplication problem, then this would be 3.1 times 2 is going to be 6.2 times 10, add the exponents to the fifth. Now, your calculator can handle that sort of problem really, really easily, but you never know. Your calculator might die. And I've never met a phone that was really good at letting you put in this sort of thing. But then I've always had cheap phones, so what do I know? Addition and subtraction seem a little bit more calculated, seem a little more complicated, but not so much. You have to line up the decimal point, basically. You can add and subtract so long as the exponents are the same. So let's go with 3.10 times 10 to the third plus 2.0 times 10 to the second. Okay. You have to get the exponents the same. And that means moving one of these decimal places. Okay, that's all it takes. So let's go ahead and shift the bigger one. We'll make the exponent smaller. That means moving it to the right. Ba-boom. 31.0 times 10 to the second plus 2.0 times 10 to the second becomes 33.0 times 10 to the second. That's all you have to do. For addition and subtraction, you're going to pretty much just bring these straight down. It's not going to change it at all. Subtraction, same thing. 31.0 minus 2.0 times 10 to the second times 10 to the second would be 29.0 times 10 to the second. No big change. Like I said, calculators can handle these. You just need to also be able to do it yourself, just in case. Also, in case you put something wrong into the calculator, it might be a good idea to be able to recognize when the calculator is feeding you a nonsensical answer. This is what your calculator would actually spit out if you fed these problems in. So it's good to have some familiarity so you know if you've made a mistake putting the numbers in, because your calculator will spit out exactly what you tell it to, even if you've made a mistake. All right. Now, uncertainty. We're still talking about measurements here, not quantum mechanics. There's a couple of things to remember to know about uncertainty. And that is that when you take a measurement, your answer isn't going to be perfect. Okay, it can't be. Okay, there's no such thing as, a perfect measurement. Okay. And I'm making a distinction here between analog and digital. Okay. What I mean by analog is something like, a ruler with lines marked on it, right? And here is, some object you're measuring. And how long is this? Well, it's 1, 2, 3, 4, 5, 6, 7. Let's pretend I'm able to draw a straight line. Okay. So the actual length is somewhere between 7 and 8. Let's call them centimeters. So you're always going to have to estimate, between the smallest markings on the analog device you're measuring with. So in this case, it looks kind of like 7.8 centimeters. So this is the uncertainty in your measurement. Okay? Just because your device isn't perfect, you aren't perfect, no matter what your mother tells you. And so you're always going to have to, just sort of do a little fudge work there. For a digital device, one that does the measuring for you, okay, it measures automatically. You'll often see this number jiggle, a little bit up, a little bit down, what have you. For any digital device, the uncertainty is always here in the last decimal place, okay? Similar to, here with the analog. So that's what I mean by analog and digital, and that's what I'm talking about, the uncertainty in the measurement. But this also brings us to the concept of precision and accuracy, and what they mean for significant figures. First off, precision and accuracy are two different measures for error. Two ways, I should say, of talking about error in a measurement. Okay. Precision talks about random error. Accuracy talks about bias. Okay. So the go-to analogy for this is always the dartboard. Okay, so we'll talk about precision first. Okay, low precision means, you have a lot of random error, a lot of noise. Okay, so here's your dartboard, there's the bullseye. So low precision means, your answers are kind of scattered all over the place. Okay, so randomly and with a lot of noise. Okay. High precision means that they're all grouped much more closely around the target. Okay. Low random error, low noise. Okay. And okay. Now, accuracy is talking about bias. So, in other words, for accuracy, low accuracy means high bias, means that your answers are all off in one particular direction. High accuracy means, once again, they're all right on target, or at least they're centered on target. Okay, because you can have high accuracy and low precision, low accuracy, high precision, and so on. Okay, so that is accuracy. Accuracy means you're off in one particular direction. Precision means you're off in random directions. So when you look at both of them together, low precision, high precision, low accuracy, high accuracy. Okay. So low precision means that you're going to have a lot of noise. Low accuracy means that your center is going to be off. So you're going to be seeing something like this. A lot of scatter, way off target. Okay. High precision and low accuracy means that you're still going to be off target, but they're going to be tightly grouped. Okay, you've eliminated your random noise, but you haven't eliminated your bias. Okay. High accuracy means you're going to be centered right on the target. Low precision means that you're still going to have a lot of noise. Okay. And because noise is random, you can be sort of anywhere within that range. High precision and high accuracy means you're right on target and you have eliminated your source of noise. So this right here is what we want. Okay? And in order to get there, that means we're going to have to find some way to eliminate both noise and bias. So precision versus noise. You have to find a way to get rid of the random influences from outside crap. So there are different ways of doing that depending on your measurement. So for example, I have worked with high precision balances, where the pan where you do the measurement is inside of a glass case in order to, prevent, random little tufts of air from coming in and jiggling the pan. And then you can measure in, like 5.237 micrograms, just a very, very small amount of matter. Okay. There are various devices that you're going to be using. You will almost never be using anything quite that sensitive. So noise isn't a huge issue in terms of the equipment. The fact that you are going to kind of suck at what you're doing is going to be a far bigger issue. So the way to eliminate noise in your experiments is to be careful. Okay. So accuracy versus bias means calibration. Calibration just means you are taking a known quantity and you measure it. You might take a weight, a brass weight that has, that has been weighed out before. It weighs 5 grams. You plop it down on the scale, and the scale says, okay, 5 grams, or what have you. Calibration just means measuring some sort of standard, and then adjusting your measurements up or down depending on how it was off, which direction it was off. Your balances will usually have a little button over here that says 0/T. That means you zero it out, or you tare, T-A-R-E. You're tearing the measurement. You're just telling it to just go to 0, and then whatever I put on there, that's what you weigh. So there are different ways of eliminating bias, but they all basically come down to calibration. So calibrating your equipment is also fairly important. Okay, significant figures, they tell you how much information is contained inside any measurement you have made. Okay. So we go back here, give you some examples. So 3.0 meters versus 3.002 meters. Okay. This one up here has only 2 significant figures. This one down here has 4 significant figures. Okay, this one contains more information. You're using a better device, one that has, if it was an analog marking, then instead of just having, lots of those, it would have, tons and tons and tons of little lines, and this right there is your estimate. Whereas this one, you're using like a yardstick with no lines on it, and measuring basically just. That's where your estimate is. It's somewhere between 3 and 4 meters, really close to 3 meters. That's terrible, right? So significant figures tell you how much information, how much actual information is contained in whatever measurement you've made. Okay? So you have to know, for various kinds of math, how many sig figs are in your measurement, where the significant figures are. Okay? So which actual digits are significant and which are just filler. Okay? So every non-zero digit is going to be significant. So for example, 11.2, 1, 1, and 2, those are all non-zero, so they're all significant. There's 3 sig figs in that measurement. 1 and 0 makes 10. The 1 is significant, the 0 is not. It only has 1 sig fig. Now, when you're looking at zeros, you have to look for certain kinds of zeros. Okay? Trailing 0 means that it comes at the end of the number, the right-hand side of the number. And if it comes to the right of the decimal place, then it is significant. Okay, so 11.0, that 0 is to the right of the decimal place. That is a significant 0, so 11.0 has 3 sig figs. But 110, this trailing 0 is to the left of the decimal place. It doesn't count. There's only 2 sig figs. Now, any 0 that comes between sig figs is itself significant. Okay? So 11.00, this trailing 0 here to the right of the decimal place, it's significant. So this 0 is also significant. So 1, 1, 0, 0, 4 sig figs. Likewise, the 1s are all significant. This 0 is between these two 1s. They are significant, so it's significant, so 4 sig figs. 1010, the 1 and the 1 are significant. That makes this 0 here significant. But this 0, it's a trailing 0 to the left of the decimal place, not significant. 1010 only has 3 sig figs. Now, knowing which digits are significant, knowing how many sig figs there are counts, matters, I should say, because you have to do math. And you have to pay attention to your sig figs, which parts of your numbers are significant, in order to get an answer that only contains genuine information. So, there are, once again, different rules for addition and subtraction versus multiplication and division. So for addition and subtraction, you have to look for the trailing digit. So let's say 4020 minus 321. Okay. Now you're going to work your way from left to right, and you're going to look for the last significant digit. Okay. As soon as you run into a number that has run out of significant digits, that's when you're going to stop. Okay. So significant, significant, significant. This 0, trailing before the decimal place, is not significant, so that is our cutoff. The 321 still has a significant figure, but okay, the extra precision, whatever it was in this measurement, let's go ahead and call them meters, the extra precision down here is lost. It's swamped by the lack of precision here. This is the estimated figure for 321. This is the estimated figure for 4020. Okay, so this could be anywhere from like 4015 to 4024. So this 1 meter here doesn't really count. It's going to get lost up here. Okay. So let's go ahead and do this math. Okay. So you just do the math like normal. 9, 9, 6, 3. And then you, this is where the cutoff is, so that means that these 3 are going to be counted in the answer. This one is not going to show up. So you round your answer. 3,700. Ooh, that's an interesting number. This actually makes for a perfect segue, because now we need, this wasn't intentional, I swear, we need to indicate that these 3 are significant, but this one is not. Okay. So that's what scientific notation is for. That's where it comes in handy. 3.70 times 10 to the third. Okay, now this 0 has been converted into a trailing 0 after the decimal point, and now it's significant. Okay. So that's, kind of a handy way to, maintain significance, to illustrate significance, I should say. Addition works the exact same way. Another way that you'll occasionally see, I don't particularly care for it, but you will often see something like this. Unnecessary decimal point. If they include the decimal point when there's nothing after it, then that means that they're saying that the 0 coming before it is significant. The reason I don't really care for this is because that is really easy to miss, but it shows up kind of all the time. So this number right here, this 200, significant 0, significant 2, it's in between sig figs, so it's significant. This guy has 3 significant figures. So that is addition and subtraction. You just work your way from left to right until one of your numbers runs out of significant figures, and that is where the cutoff is going to be for the significant figures in your answer. Now, multiplication and division, as you see here, it doesn't care about the trailing, it's just the total number of significant figures. Okay. So, for multiplication and division, let's say 379 divided by 4.0. This number, 4 and 0, it's a trailing 0. After the decimal place, this has 2 sig figs. 379 has 3 sig figs. Your answer is going to have the lesser number of sig figs, the smaller number of sig figs. So your answer is going to have only 2 significant figures. So we'll go ahead and do our division like normal. Ignore this for the moment. 437.9. Okay, and now we can go ahead and stop there because we know it's going to be 2 sig figs. So we're going to have to round this number to 95, and that's our answer. So with addition and subtraction, you care about trailing digit, the trailing, whichever one runs out of sig figs first, and for multiplication and division, it's the number of sig figs. Now, last thing for today is dimensional analysis. Dimension is just another word for unit. So 5 kilograms, the units are kilograms, that's also the dimension. 5 joules, the joule is the unit, the joule is the dimension, but you can also write that as kilogram meter squared per second squared. Those are also the dimensions. Okay? Dimensional analysis is a tool for problem solving because it's a way of trying to understand the information you've been given in the problem. So you look at the problem, you say, what information do I have, what information do I want, and how can I get from what I have to what I want? So you look here, just a random-ish example. If you're driving a car that weighs 3,000 kilograms at 52.4 kilometers per hour for 2.5 hours, and you get 31.7 kilometers per liter. How far did you travel? Okay. All right, so we have all this information that's been thrown at us, and we need to look at what we have and what we want and how we can get from one to the other. Now, how far? That means we're looking at a distance. We need kilometers. Okay, so 3,000 kilograms, kilometers per hour, hours, kilometers per liter. Well, kilograms doesn't help us at all. We don't need to know the weight of the car. Okay, 31.7 kilometers per liter. The mileage the car gets might help if we knew how much gas they had used, but other than that, we cannot get to distance from there. But kilometers per hour and total number of hours is going to help. What we can do is 52.4 kilometers per hour times 2.5 hours. Hours will cancel, and you're going to be left with, let's see, a total of 78.6 kilometers. Is that the answer? No, because this has 3 sig figs, this has 2 sig figs. Your answer is supposed to be 79 kilometers. The lack of precision in that measurement kind of messed up the precision in that measurement. So that is dimensional analysis, just a really, really quick walkthrough. You have to look at the units. If you have a lot of trouble with word problems, I recommend go ahead and circle or underline or highlight the measurements that you're given in any problem, and then look at the units of each of the measurements given and compare those to the answer you're looking for, so that you can try and work out a path to get from A to B. Okay. And that will do it for today. Some of you may have noticed that I made a mistake there at the end of the lecture. In my defense, this is my third attempt at recording this darn video, and I was eager to be done. So, what I actually did, that's the problem, the flaw of working in your head is that you don't necessarily see your mistakes. I multiplied by 1.5 instead of 2.5. The actual answer should be about 130 kilometers. So for the sharp-eyed among you, good for you. You get a cookie. You'll have to get it yourself. And now the lecture's done. Go away.